Welcome to Lecture 2 of the course Sustainable Energy Management and Efficiency for Data Centers. In this lesson, we dive into the physical and functional components of a data center, with a particular focus on where and how electricity is consumed. Data centers are facilities that house IT equipment, including servers, storage systems, and networking equipment. To ensure these subsystems to continue to function properly, data centers require additional components, such as cooling system, uninterruptible power supply batteries, backup power generators, and auxiliary equipment like lighting. Now, let's break down each component. The main electricity consumers in any data centers are servers. These units execute applications, process data, run machine learning algorithms, and provide line services. They can be equipped with the central processing units and specialized accelerators, such as GPUs. On average, servers account for about 60% of the total electricity use. Storage equipment plays a supporting role by storing and retrieving digital content. Although less power-intensive than servers, storage systems run continuously and contribute about 5% of the overall energy consumption. The energy demand from this component varies depending on data volume, backup frequency, and type of storage architecture. Networking devices, such as switches, routers, load balancer, and firewalls, ensure data moves within the data center and to outside world. While individually less power-hungry, this system must be continuously active, ensuring low latency and secure data transmission. Their contribution is typically about 5% of the total energy use. Cooling and environmental controls consist of equipment that regulates temperature and humidity to keep IT equipment operating in optimal conditions. IT equipment generates heat as it operates, and this heat must be removed to prevent damage or performance degradation. On average, this equipment accounts for about 60% of the total electricity use. Uninterruptible power supply batteries and backup power generators keep the data center power during outages. These are rarely used but are necessary to ensure the extremely high levels of reliability that data centers must meet. While this category may only represent about 1 or 3% of the total energy use, its importance is extremely high. Without reliable backup, uptime guarantees cannot be met, and data loss could occur in the event of a grid failure. Other auxiliary infrastructure include lighting, monitoring, and office support systems. This figure shows the breakdown of the energy consumption of the various subsystems for the different types of data centers. Enterprise data centers consume a significantly portion of the energy for cooling, which can be represented for up to 30% of the energy use. This high consumption is often due to inefficient airflow management and the use of outdated cooling systems. In many cases, both the IT hardware and the physical layout are outdated, leading to inefficiencies at both the component and architectural levels. As a result, the share of energy consumed by the IT equipment is relatively low, typically around the 50%. On the other hand, hyperscale data centers show a very different energy distribution. These centers are designed to be efficient. Here, IT equipment can account for 70% or more of the total energy consumption. This is made possible through high server utilization, advanced workload orchestration, virtualization technologies, and high-efficient cooling systems. In such environments, cooling typically represents only around 10% of the total energy use. Finally, colocation data centers fall somewhere between these two extremes, with energy use patterns depending on the specific infrastructure and client deployment models. To quantify these loads over time, we can refer to the given equation, which is a simplified energy balance for data centers facilities. The total power demand at a given time on the left-hand side of the equation is expressed as the sum of the contribution of each equipment. The terms on the right-hand side of the equation represent respectively the load from the IT equipment, the load from the UPS systems, summed up with the losses in the power conversion, the load from the cooling systems, and the power consumed by the auxiliary systems. However, not all components of the data center behave similarly over time. While some loads remain relatively stable, others fluctuate depending on the external conditions and workload patterns. This behavior is evident in the figure, which illustrates power consumption profiles for a data center over the course of a year, divided by subsystems. Though this data is simplified and synthetic, it provides useful insight into how various energy uses behave over time. In the plot, the blue line represents the IT equipment load, which is stable over time. This reflects the continuous operation of servers and storage, which are usually maintained at a steady state. The red line instead represents the cooling load, which shows strong seasonal and daily variability. This variability reflects the dependence of cooling system on external temperature and internal heat load. Understanding how a data center uses energy and how this energy is distributed among its various subsystems is essential for identifying where efficiency strategies can be most efficiently applied. The relative impact of each component, from servers to cooling systems and support infrastructures, depend heavily on the type of data center in question. Tailoring energy efficiency efforts to the specific characteristic of each data center type allows for more targeted interventions and more meaningful reductions in the overall energy use. In the next lesson, we will introduce the key metrics used to assess energy efficiency of data centers. These indicators are critical tools for benchmarking performance, identifying inefficiencies, and guiding both technical improvements and strategic planning.